Good evening to all. Welcome to our OpenPOWER Academy and Research webinar. As part of this webinar today, we are going to have the Open Power Hardware related talks. And thanks for joining today's webinar, and my pleasure to have you all here. Today's session is going to be covered by our last speaker, as part of this Open Hardware collaboration, Vinod, who is actually part of ISDL India. The IBM, the SME, on power architecture. He's going to be covering the PowerPC assembly language introduction, which includes PowerPC application binary interface, and also the PowerPC application programs. So after Vinod's talk, the Shivam, one of the the students in India, will be sharing his experience at DAC and also plan forward with the IBM, the Open Power core, the A2I core. With this, I'd like to invite Vinod to go ahead and present. Vinod, please go ahead.
Thanks, Ganesh. I'll share my presentation. Okay, are you able to see my screen?
Yes, Vinod, go ahead, please.
Yeah, sorry for the delay. I think I got a new laptop set up, so he was asking some permissions. Sorry for that. Okay, so I'm going to start with application binary interface. So last time we did cover about instructions, PowerPC instructions, book one instructions, registers, and then it has descriptions of all instructions. So whenever we write an assembly program or we write in other languages like be it C, what happens underneath is it like if you write a program in C, it gets compiled, and then as you guys know, uh, it'll you will generate an assembly language, then you will generate a binary code, but the intermediate step is assembly language is generated. So there is an application binary interface, or there is a protocol of, like how each routine interfaces with the other routine, or in other words, what is the convention of the register usage. So there can be programs where, some of the functions you write can be in C and some of them can be in assembly. So what can happen is you can call an assembly function from C program, and then from a C function call, and then from a C function call you can again call an assembly function call. It all depends on the application and then the different routines you are writing and the function calls that are happening. At least in the low level area, like when the operating system is being when the coding is done for operating system or for the interrupt handlers in the operating system. So these kind of things are very common to write in assembly language and C, and then call a routine from C, assembly language routine, and from an assembly language routine you can call a C routine. But when you go to application space, maybe it's less of assembly language, but then whatever I'm talking today is still taken care, even when it needs to be taken care when even we write we write C programs. but then the user or the coder may himself not take care, but then the compiler or the assembler and stuff like that, they take care of the register convention, which registers need to be used in the assembly, and how do we need to take care of the registers. So I'm going to talk over it. So as we have seen last time, there are registers called general purpose registers. So we have 31 registers, and each of them is of 64-bit length. So whenever we write a program or in the C under the covers, the way these registers are used, is described here on the chart. So first register is the GPR0. So this register is a volatile register, and it is used in function prologues. So when we tell some register is volatile register, what it means is when you call from one routine to another or one function to another, you are like a function A is there, then you have invoked the function B. So when you come to function B from A, you can't expect GPR0 to have some value. It's volatile. You can't tell that, it should have a particular value. Or in other terms, take another example. A calls B, and then again from B, suppose you call C and then you go back to A or something like that. When it comes back to A, you can't expect R0 to have some value. If you want to use R0 in that routine, GPR0 in that routine, you need to load the register, or you need to set the register with that value and only then use. So that's what is volatile register. Volatile meaning, you cannot expect it to have or retain some particular value. You need to build that value into the register if you want to use it. Then the next register is GPR1. This is like this register is used for stack pointer. So as we all know, when we do a lot of function calls, so when we call a new register, when new function call, then a stack frame is created and all the registers are saved, updated, and then when you return from that register, you can that stack frame use that stack frame to return the values and stuff like that. So GPR1 is used to track the stack pointer. So whenever you do a function call, the GPR1 gets updated to the stack pointer of that function routine. So that's how GPR1 is used. Then GPR2 is for talk pointer. Talk pointer is a table of contents. And then there's something, like if you, a table of contents is in line with the GOT, global object table. So what happens in global object table or talk table of contents is the programs which we return write are actually relocatable. So depending on the operating system, when it schedules that application, and depending on how many applications are running, and depending on all other things, they may be actually at a particular place in the where they will be in the memory, or where they will be running from the memory, or physical memory, virtual memory. All that is not fixed. It all depends on the runtime. So these programs are actually relocatable. So the stock and GOT these take care that that the program is relocatable. They have the addresses, they have the corresponding addresses, and you can work on them. So that's how GPR2 is used. Coming to GPR 3 to 13, these are again volatile registers. So you can't expect them to be saved or unsaved. So if you want to use it in any particular routine, you need to make sure that you set the values to them. And when one function to another function call is invoked, GPR 3 to 13 is in general has the parameters which we send. So we write a function call, we can have different number of arguments. Suppose we have 3 arguments, they will use for those 3 arguments, they will use register 3, 4, and 5 to pass those values. So GPR 3 to 13 are generally volatile registers. They are used for parameter passing from one routine to another. Coming to GPR 14 to 31, these registers are preserved across function calls. That meaning they are non-volatile registers. So when across the functions, these registers need to remain. So from one routine to another, it shouldn't be that 14 to 31 values change. So what that means is, suppose somebody uses GPR 14 to 31. Suppose I write a assembly function, uh, add two numbers or multiply two numbers or Fibonacci series, whatever I write. Suppose I am in short of the registers, like 3 to 13 are volatile registers. I need not save them. I can use in my routine and then work on them. But I need more registers, and for me 3 to 13 is not sufficient. I can go ahead and use 14 to 31, but before using, I need to save those registers. And after the logic or whatever I need to do in my function, after I'm done with it, I need to restore those registers and then return from the function. So you don't assume GPR 14 to 31 values in the register to be corrupted, or you don't expect them to be overwritten. They are non-volatile. So you need to make sure that in your function call, you don't change those registers. So this is about general purpose registers. So if you basically see GPR 0 and 3 to 13 are volatile registers, 1 and 2 are used for specific purposes of stack and talk. 14 to 31 are non-volatile registers, and these registers need to be preserved from function call to another function call. Then moving on to floating point registers. So there is a similar convention in floating point registers. So I'm not going to go in detail about volatile, non-volatile. So I'll quickly walk you through here. So F0 is a volatile scratch register. So here you don't expect value to retain. Similarly, F1 to F4 are again volatile, and these are mainly used for parameter passing and also return values. Whenever you return from a register, these registers will, whenever you return from a function call, these registers will be used. Coming to F5 to F13 are again volatile, and these are also used for parameter passing. And F14 to 31 are non-volatile registers. Okay, so moving to next slide. So there are some registers which are special purpose registers. We did touch about this in our last presentation too. So link register is basically used for making function calls. You can branch on a link register. Basically, you can load an address in linked register and you can do a branch so that you can go to that address or that function call and then start executing the instructions from there. So this register is volatile, so you can't expect from across the function calls to retain the value. So before using, you need to make sure you have proper value. And there is another register called CTR or count register. This is mainly used in loop. So you can, like in a for loop, if you see internally, you go and see an assembly program, you can use assembly compiler or assembler can actually use a CTR count register. So when you tell for loop I to 100, he can actually use a counter or counter register, and then he can loop. And when that register becomes 0, he can come out. That's how this counter register can be used. From the loop, he can come out. And then XER is fixed point exception register. So even this is volatile. So this register basically has this register, there are various bits in it, and they get set when some kind of exception happens. Some things like you do 1 by 0 or infinity, you do some things different. This register, there are status bits which get set in that. And for floating point, there is FPSCR, floating point status and control register. This too is volatile, and this register mainly has status and control bits for a lot of floating point operations. Like in floating point, you have different modes for rounding. You can round to 0, you can round to infinity, you can round to minus infinity. you can round to a nearest number, for all of that stuff, you can mention in how your program should behave by setting corresponding bits in floating point status control register. And there are even bits which tell if there is any exception that has occurred when a floating point operation has happened, or if underflow has happened, overflow has happened, like when you add numbers or when you subtract numbers, if there is underflow, overflow, or if there is an exception, all of that gets recorded in floating point status control register. And there are also bits which tell whenever there is an exception, how should the program behave. Should he take an interrupt, or should he not take an interrupt? All of that settings are there in this register. Moving on to the next section of condition registers. So condition registers are mainly used when you want to compare. So you want to compare two numbers, be it floating point or fixed point numbers. So most of the times in our programming, we have to compare numbers like less than, greater than, equal to. So these condition registers, when you compare the result, you can for the compare instructions, these condition registers or the CR fields in the condition register are the arguments to that instruction. So you can specify which condition register field can be set, and in each of the condition register there is a equal to, less than, greater than, all of these fields which get set depending on the operation. If the value was, if two registers are compared, if you got lesser, which register is less than which register or greater than, and depending on those values, the which bit gets set. Generally in programs you can branch off or you don't branch off, all of those operations happen. So CR0 and CR1 fields of the condition register are volatile, and CR2 to CR4, that is CR2, 3, and 4 are non-volatile, and C5, C6, C7 are again volatile registers. So briefly speaking, these are the conventions that need to be followed when between different function calls, be it C to C function call, or assembly to C, or C to assembly. So if somebody is specifically writing only C code, these conventions still are to be followed, but they are taken care by the compiler and then you won't see it. But in case you need to write assembly, you need to take care of these things, that if something is non-volatile, make sure that if you are using, save it, then restore it, and then go back. These are the different conventions you have to follow. Then I would be moving on to the next section in my next chat. So basically I have taken some simple assembly programs. I can walk through it or describe about them. So this is a simple assembly program where he is basically, the LBZ is a load byte 0 instruction. So from the memory, he will load a byte. So here R3 is the register which has the address, and 0 is the offset from that address where you want to load. So here you are telling, you want to load from basically whatever address is present in R3, and you will load into R4 register. Then he's comparing whatever value has loaded in R4, he's comparing it with 0. So if R4 is 0, he is telling he'll branch off to done. Otherwise, he's going and adding R4 with the hex 20 value, that is decimal 32. Then he is storing that value into the same address, whatever is there in the R3. Then he is going and incrementing R3. That is, he is basically going to the next byte, and then he'll loop back to the start of the routine. So, and he will do this until he will see R4 is having a 0. So this is a simple assembly program where you are loading from memory. You are just incrementing the value of the byte that is present in that location by 32. And then you are moving on, and you do until you encounter a 0 in the addresses which you are doing a load from. So this program is a simple program, but this can be used, if you think about it, this can be used to convert a string of capital letters to a string of lowercase letters. If you guys know the capital letter and the lowercase letter, if you consider the ASCII values of those letters, hex 32 is the difference. So here, if you take a string of capital letters, and then you can end the string with /0 or 0, right? Then what happens here is you load every byte. So you are basically loading every letter. Then you are incrementing the value of the byte that is present there by hex 20, or the ASCII value is incremented by 32. So you basically made the letter into a lowercase letter, and then you stored it. So this program, this assembly program, can be used to convert capital letters into lowercase letters. So this is one routine. Then I'll go to my next small program. Okay, so here we are using, as we spoke earlier, we are using count register. So I will counter register. So I'll go through it. So you are loading here R4 with 100, and you are moving that register into CTR. Move to CTR will move whatever is there in R4 into this counter register. Then you are doing a load from R5, load into R5 from register R6. So earlier you have seen that we have used a register and then the offset was 0. So here we have it 4. So we are loading from an offset of 4 from a particular address, and we have that value into R5. Then we are adding whatever is there in R5 into R7. Whatever is there in R7 and R5 we add and store it in R7 itself. Then there is a branch, and this branch, what it does is it's checking if the CTR is 0 or not. So if it is 0, it wouldn't do anything. If it is non-zero, NZ is for non-zero, then it'll branch back to loop. So it'll also decrement the counter. This guy also decrements the count, like in the CTR. So this branch instruction, that's how the implementation of this branch instruction is. So he decrements the counter. He checks we checks whether the counter register is 0 or not. If it's non-zero, he'll go back and he again loads. So he will do this loop until the counter becomes 0. So this is an use case of how counter register is used. So here, if you observe, this load is load word 0 update. So this is an load instruction also and an update instruction also. So it will load R5 with a value which is present in this address R6, whatever is the address in R6, and an offset from there by 4 bytes. Whatever is there in that address, he will load into R5. And at the same time, he updates the register R6 with R6 plus 4. So the address plus 4 bytes. So that's the reason this instruction is load and update. So R6 basically is updated with a new address or a new value. And whenever you are loading, so in this loop, whenever you are loading, so what is happening is you are loading actually every time from next 4 bytes. And this is a load word. So you're basically loading a word every time, and next 4 bytes will take you to the next word. So you do this loop till your counter becomes 0. So these are different concepts which are covered in this program. Then I will move to my next program. Okay, so in this program, this is something similar to the earlier program, but it's a little bit different. So here we are using floating point registers. So what happens here is we are again using the counter. So we are again using the counter, loading R4 with 100, and we are moving that counter into, sorry, we are moving R4 into the counter. Then we have an instruction subtract, where from R5 register, we are subtracting 8 bytes. We come down, we are doing a load floating point double word. So into register F0, we load from address R6. Then we are doing an add-I here. We are loading R6 with value 8 and storing it in R6 itself. Then whatever is there in register F0, we are storing at an offset 8 from the register R5. And we'll come back and we know our counter example where we will loop through this until counter becomes 0. So we have basically whatever is there in address R6, we are storing into a place where to an address which is there in R5. And every time we increment R6 by 8, so that we are picking up the next 8 byte, next double word address from R6. So R6 is updated every time. And if you see here, we have used stfdu. So here, this does a store and also an update. So it'll basically, whatever is there in R5 register, it'll update with 8 bytes. It'll add 8 bytes to R5. So it'll update the R5 register. And whatever is there in F0, it'll store into the address, whatever is there in 8 R5, 8 plus R5. So for R6, we are manually updating the address. For R5, this instruction itself is doing the update. Then if you notice another thing, we have actually subtracted R5 here with 8. This is done because when you do a store here, he'll store into 8 plus R5. So that is the reason you are subtracting initially itself R5. See, you want this 8 to be updated every time. You want 8 plus, but you want to start at R5 address initially, whatever is there in R5. So to make sure that you update also and even store from the R5 register itself. So initially R5 is subtracted with 8. So you still are, when he does a 8, you actually come to an address wherever you want to actually store. So he will update. So in this both counter, then, update instruction, then branch for non-zero depending on the counter. So these are all different things which get covered. So these are some, simple programs. So I thought I'll go through it. So we covered in this session register conventions, and then how do we use those registers if we write assembly, or even if we are writing compiler, you need to take care of this convention, and small sample programs which tell how general purpose registers are used, how counters are used, and then how branches is used. So in this branch, if you see, so basically here you are also using the count register, branch on count register. So these are all different concepts. And then the update instructions, which will update the registers and also do a load, also do a store. Okay, so these are some things, I thought I'll cover in this session. Thank you.
Vinod, thank you very much for your session. Really appreciate it. Participants and panelists, do you have any questions for Vinod? Abhishek? Shivam?
No, sir, nothing from my side. No.
Anything? Any questions from participant? Please go ahead and raise your hands, or you can also use the question and answer session, window to pose a question. Any other? Miss, I welcome Professor Gopal from Anna University, to be part of this webinar. Sir, you have any special question for this webinar or anything you want to say? Okay, Vinod, there is a question from one of the attendees. How does the counter register changes in the loop?
Yeah, so what happens is this branch instruction which I was showing. So what it does is it actually decrements the counter register also, and it keeps checking if it's 0 or non-zero. So when it is non-zero, it will loop back to wherever you wanted to go, like to the label you wanted to go. And whenever it's whenever it's 0, he will go down or to the next instruction. So he won't loop back anymore. So the branch instruction is doing a couple of things. One is he's decrementing the counter register, and then he's checking on the counter register and checking whether it's a 0 or not, and then looping back. So that is the answer.
Okay, thank you, Vinod.
Thanks.
Any more questions?
I have one. Vinod sir, is there any standard textbook as such for Power? I mean, we know of MIPS. For MIPS and RISC-V, we have Pattison and Hennessy.
Yeah.
So apart from the manuals, is there any book as such?
So actually, instruction set architecture, the document, actually, I was sharing that in my last presentation. I can again send you the link on the web page. But that in detail, it describes each instruction, the registers, and then what each instruction does, what registers it uses. So it is a very, it's like a manual. It has everything in it.
Right. Thank you, sir.
Thank you.
Any other questions, participants? Yeah, this is a good opportunity for you to interact, and going forward, I want this session to be more interactive. This is a core team we developed, right? As part of the OpenPOWER and the processor development. I think this is a great opportunity for all of you, to learn and start working on a deployment too. We are going to have a lot of parallel threads, as part of this from the basic, and there are some people who have already done some good work, and definitely you're going to see that from the next presenter who is a student here, Shivam, who is going to be sharing is DAC, Design Automation Conference, which was held last week in San Francisco. That is going to be sharing a little bit, and then he is also going to share what he's planning to do as part of this, the whole initiative. Shivam, please go ahead. Start your presentation.
Yeah. Is my screen visible to everyone?
Yeah, looks good.
Okay. Hello, everyone. Thank you, Vinod sir, for the informative session. Thank you, Ganesan sir, for giving me this opportunity to speak. I'm happy to see many of my juniors from NITK and some of my friends on LinkedIn who are part of this session. I hope this helps everyone in some sense. So what I'm going to do is I'm going to talk a bit in general about OpenISS and the projects around it. As I said, I'll be presenting. I'll just show, and maybe if people are interested, I would go a bit into the details of the poster which I presented at DAC this year, and then we would have a basic roadmap of sorts about what we are planning to do around the open source, open power cores, which are already released by IBM or the community, right? And at any point, if you have any questions, please feel free to put them in the chat or any discussion points as well, right? So starting with a little bit history about OpenPOWER ISA. So these are some facts. Mostly I took them from Wikipedia, but I thought it's a good idea to know, a brief about, what we are looking at. I think most of you might have some idea about OpenPOWER already, but OpenPOWER is basically an ISA which is released by IBM. It used to be a proprietary ISA, and then it was released to the open source community recently. One of the very good facts about Power is it is one of the ISAs which powers many of the supercomputers in the world. The recently released A2I core is also part of one supercomputer. We'll be talking about it more. So these are some facts about it. Yeah, then RISC-V is another popular open source ISA. The reason I'm talking about RISC-V is the poster which I'm going to present has a bit of background on RISC-V. So I thought I'll just give a short introduction. So Power is something which has been around for almost 30 years now. It was started by IBM. Then there was a alliance which worked on it. There have been a lot of silicon processes around it, and then it was later, made open source. RISC-V is something which is very recent. It was released it started in 2010, first as an academic project and then released to the open source community. And now it is being maintained by RISC-V International. It is still at a very nascent stage, but silicon adoption has started. There are companies like Sci-Fi, Western Digital, Nvidia, Microchip, Alibaba. From India specifically, we have CDAC, IIT Madras, and there's a startup called Incor out of IIT Madras, which is working on RISC-V processes. And both are, both are different. It's not really a competition as such. Both have their own good and bad things. Right. So coming to the DAC poster, DAC is basically the Design Automation Conference, which normally takes place every year in San Francisco. This year, obviously, due to COVID, it was a virtual conference. And I was one of the DAC Young Fellows. So DAC has this program where it funds students up to PhD level who can go physically to the conference. They can attend all the sessions, and they are also given some career development and in general presentation opportunities. So one of these things in the program was a poster presentation where I presented my ongoing project. I'm actually working as a GSOC student with Free and Open Source Silicon Foundation, and the project which I presented is currently work in progress. And this is the poster around it. So if I'll try to give a short introduction about it. Basically, we are trying to work on a multi-core system. So we have, most of you might have heard of Verilog and VHDL, which are your standard hardware description languages. So we have this new language called transaction level Verilog, which is, in some sense, it is one level above in terms of abstraction. It's a bit different from high level synthesis or say languages like Chisel. It is, in a way, you can say it is still Verilog, but at a higher abstraction level. You have timing abstraction, which is one of the biggest features, and it makes things like designing a pipeline processor very easy. And on the other side, we have the system called OpenPython, which is made by Princeton University and is also open source, which which is a framework apart from the CPU core itself. It is a base framework for multi-core systems. So when you say build a quad core processor or something of that sort, apart from just the cores, it needs a lot of other technical parts, which is cache coherence. Then you have interface with external components such as memory and etc. So all that requires a good amount of hardware, which has to be multifunctional. And OpenPython is specifically made for heterogeneous ISA research. Heterogeneous in the sense you can have cores of completely different ISAs connected to the same system and working with each other. So as you can see in this diagram, as of now we have one core which is in Spark, one is in x86, one is in 2R and RISC-V, and then WAF5 is a work in progress which is being integrated. And probably very soon we'll see even a Power ISA core which is integrated in OpenPython. Right, and talking about project opportunities with OpenPOWER, there are plenty, because as now it has become an open source initiative. People all over the world are collaborating on it. All the projects, you would find them being open sourced on GitHub. You can right now, go to GitHub, search for OpenPOWER core, download the whole code base, and try to learn through it, try to work on it. And these are 3 open source power cores. There might be others too. I'm not sure, but these are like the popular ones. One is microwatt, one is chiselwatt, and one is A2I. Microwatt and chiselwatt are in some sense small scale. They are more suitable to be called as soft cores, which are meant for FPGA implementations. I don't think there has been a silicon implementation as of now. And yeah, so both of these are open sourced on GitHub. Microwatt is in VHDL 2008. It has all the support for Xilinx FPGAs such as Arctic 7. Chiselwatt, as the name suggests, is written in Chisel, which is another new HDL by UC Berkeley. Even that has a open source. So GSDL is open source simulator. Even Verilator is open source. So you can actually see the waveforms and stuff right now in your PC. If you go to the GitHub repositories, it has good instructions about how to set this up on your local system. Apart from that, Chiselwatt also supports open source FPGA toolchains as well. So there are toolchains like Yosis and XPNR which support ECP5 based FPGAs. ECP5 is itself a FPGA whose bit streams are open sourced. So there are various boards based on this FPGA which are supported by Chiselwatt. And then A2I, being the most recent one, is also the most powerful open source open power core which is available at the moment. It was used in Blue Gene Q, which is a part of many of the supercomputers even today. And even A2I is in VHDL. Even that is available on GitHub. One of the prominent features is that Microwatt and Chiselwatt are soft cores, but A2I is actually implemented on silicon. It has been tested in supercomputer level multi-core systems. So that it obviously works, and it is it supports frequencies of the order of 3 gigahertz. So obviously it's a multifunctional core. And A2I is actually much you can say larger than these two. These can be implemented on very small FPGAs like Arctic 7 or ECP5. A2I would need quite big FPGAs like say Genesis 2 or something. People in the open source community are still working on A2I, but definitely one thing is very clear, that it would need bigger FPGAs. So if they can either be used in the cloud, or if you have say academic support, but at least simulation is something which you can try out right now. I think many people in community right now are working on A2I for open source support as such. So the potential roadmap, this is basically an outline of what possibly can be done around these cores and open power in general. We have a community in some sense which is being built right now. Ganesan sir, Abhishek are taking the efforts to address this. We have a WhatsApp group, we have a LinkedIn group which has quite a few members, and new people are joining every day. So those who are interested, you can obviously collaborate. Obviously, even people like Abhishek and me are not really experts. We are also students like you. We are trying to learn things, and we are just taking the effort to lead this. But obviously, we are not the experts. We have experts like Ganesan sir and Vinod sir who can obviously guide us. And then since it is open source, you'll obviously find resources everywhere. Yeah, I'll address one question which is there in the chat, and I'll come back to this. So someone has asked that what is a soft core? So software is basically something like one part about building a CPU is just the hardware description, which you would write in say something like Verilog. So that is just a hardware description, which you can then synthesize into a netlist, like basically the actual hardware structure, which in terms of gates or something, and then you can make an actual silicon chip. So this is called as ASIC. Then before you do that, you can actually, after you have the HDL, you can deploy it on FPGAs, which is not really not silicon implementation in ASIC sense, but you are actually putting it on hardware which is reconfigurable. So that is a soft core. I hope that answered your question. Yeah, so coming back to the roadmap, I think A2I is something which is really complex for any beginner. I think even I won't be able to understand everything out of A2I, but at least microwatt and chisel watt are small course which can be looked at as educational course in some sense. So we can start with learning VHDL, chisel. We can look at how GHDL and Verilator works. These are all open source tools, so you can easily find resources. Then you can learn about FPGA toolchains. At least the small FPGAs like Arctic 7 can be used freely with Xilinx toolchains. And then there are other open source FPGAs as well. Then you can work on simulation with these once you know how to work with GHD and Verilator. And most of the toolchains are all, I mean, most of these scripts and everything is already available in GitHub. It's just about trying it out, understanding how it works. Once you know what PowerPc is and what are the instructions and stuff like that, you can write your own programs or say build some test programs and all that and try it out in simulation. The next step can be FPGA implementation. Microwatt and chisel watt is not really difficult to implement on an FPGA. Most of you would find a FPGA suitable for them in your college labs. And then we can even add microarchitectural extensions to these. Since the whole code base is open source, you can say connect it with some machine learning accelerator or add an interface like say for specifically for microcontrollers or something like that. There are many hardware modules as such which are open sourced, and then you can integrate them with this course and try to learn if that's your interest. And then once people are comfortable with these two courses, obviously we can go to something as big as A2I and then try FPGA and extensions on A2I. A2I is, as I said, it is a bit more complex. So finding a physical FPGA might be difficult, but we can possibly do it on cloud because cloud FPGAs like LVO series which Xilinx provides on say AWS or Nimbus Cloud can be used for such purposes. Yeah. After this, sorry. Yeah. So I have a list of some basic resources around say HDLs and computer architecture in general. So all these three courses which I presented are available on GitHub. You can just search their name and you would find them in the top Google results, or you can just go to GitHub and search directly. For VHDL and Verilog, there might be better resources, but there are these books by Brogche Lamaris. The books are available for both VHDL and Verilog, and there are some YouTube videos too. I think Springer released them as free recently because of the COVID crisis. I'm not sure if they are still available. On Coursera, you have this course called HDLs for FPGA design by UC Boulder, and there are other courses around FPGA and digital logic too. For computer architecture, basic understanding, as I was talking to Vinod sir, this book would be really great. If you are not very familiar with the basic concepts of computer architecture, like how a processor works, what are the parts of it and stuff like that. This the latest edition is based on RISC-V. There are older editions which are on MIPS, but I think any of them is fine as long as you get the basic concepts. And then as Vinod sir said, there are PowerISA manuals which are detailed manuals about every single instruction which PowerISA has, and other things like software and firmware around it. And for the open source tools which I talked about, you can look at their documentation and open source projects around it. Yeah, so just a small part about how, in which direction open hardware is leading. So many of the courses are available right now. Many people are working on say RISC-V or power based course. Since the ISAs are already open source, many of them are already available on GitHub. The next step is SOCs, which obviously are lesser in number than the CPU course. I think many people are working in this direction, and if you're interested, you can obviously pursue this, like building system on chips, which adds a lot of things like memory interface, say display interface, and things like that. Basically, just a CPU core itself just has say control unit and ALU, but you need interfaces to the external world, and that's what a SOC stands for. So that is one thing which many people are pursuing right now. Then heterogeneous systems, as I said, is a interesting area for research. Like till now, we have had say 16 core Intel CPU or 4 core ARM CPU. But imagine something like you have 4 cores and all 4 belong to all 4 different ISAs, and all of them specialize in different areas. So that kind of a system would be really great. Then there's work going on open source RTL to GDS flow. As I said, we are talking about chips some time ago. So most of the software tools which are meant for building actual silicon chips are made by commercial developers, which are not easily accessible to students or the open source community. But there are many people who are working on this complete RTL to GDS flow. So basically, right from writing Verilog to the actual physical design, there are people who are working on building tools around this. OpenLane is something which was announced last week. If you're interested, you can go and search about it. Even this is available on GitHub. Then adoption is one another trend which we are seeing is adoption of open standards is becoming an industry direction. Many big names are pursuing open source hardware. Many of the brands such as Google and others are part of both RISC-V Foundation and OpenPOWER Foundation. That implies that they are really interested in taking this forward. And since it is open source, we have worldwide collaboration. And then another point is making in India. Since we have all the resources now, we can try at least designing in India, if not fabrication at the moment. Yeah, and I again thank Ganesan sir and Abhishek for leading this effort. I'm, you can say, a newer member here, but Abhishek also has been doing a lot of work around social media for the community. Ganesan sir obviously is the person who has invited us to join this effort and is guiding us about this and providing us with resources and all the required support. Yeah, and coming to questions which are okay. There's just one question, I think. Can a single core have 2 ISAs? Yes. So that is what a heterogeneous system is. So as I explained about OpenPython, if you are interested, you can go on, you can Google about it. There are 2 or 3 papers, and also the code itself is open sourced on GitHub. It is possible you can have a system where there are multiple cores which belong to different ISAs. That's what OpenPython is working in the direction of. I'm not sure if there is a production system or a existing commercial core where you have such a facility. There are cases where you have, say, cores of same ISA with different facilities. I think that's done by ARM, where you have, say, when it is a quad core system, you have 2 cores which run at different frequency and 2 other cores which run at different frequency and some different configuration. That kind of systems do exist, but I'm not sure if there are systems with completely different ISAs as such. But OpenPython is definitely a silicon-proven approach to do that. Yeah. Any other questions or points of discussion does anyone have?
Yeah, Shivam, thanks for the wonderful, the drive, and also some details, you are given already. That's very good. And, it's a good, the seed, you are seeding also, hopefully, all our students who are all part of our group, would get motivated and, and create something, as per your roadmap, or they can also add on few things, on top of your roadmap. And I really appreciate it, the roadmap, whatever you suggested. And as you said, Nimbex and, the AWS, and also I'm also putting together, some other places where we can have these kind of FPGAs where people can, students and developers and collaborators can go and get access to it and start trying something, which are really, creating some advantages for them to, getting skills or, on this platform. It's an open source platform, right? And also they can also come out with, some good, design of a processor or a core, or at least, something like a microwatt kind of, platform. So hopefully, that will happen. I would say, in a series of webinar, which I'm going to arrange, in next probably 2 months, 3 months time frame. And we have a core team as well as we have a expanded team also as part of India. And I do have some plans, in Europe as well as in US, to create teams like this. Probably one day, I may bring in, some collaborators from US and Europe to come and present in this venue too. So it all depends, how we are going to go forward and all, based on various contributors we have here. And there is another question, Shivam, from the same person.
Yes,
Attend.
I'll try to address that. So Pulpino, as far as I know, is based on only RISC-V. I think what you're confused about is RISC-V ISA extensions. So see, RISC-V is one ISA, but there are extensions for that. So RV32i or RV64i are the base extensions which support, say, only integer type of operations. But then how they have planned out the ISA is there are single letter extensions. So the basic RV32i core will have something, say, like 50 instructions, but it won't have features like, say, floating point operations or multiplication and division and stuff like that. So to add that, you have M extension, F extension for floating point, D extension for double precision floating point and things like that. And there are many others which are coming up, say vector and all for matrix operations and stuff like that. So I think Pulpino can support multiple extensions of RISC-V, not really two different ISAs. What I'm talking about in terms of heterogeneous is, say, RISC-V and ARM, or say RISC-V and OpenPOWER on the very same chip. I hope that answers your question.
Yeah, thanks for the detail again, Shivam. So any other questions, audience? I think we're almost, going to be 1 hour, closing that. But anyway, this kind of, platform always, welcoming other students also, to come and present, what they have done and what they want to do. This is a platform where, you can take your standards, your skills, to internationally. Certainly, there are a lot of people watching this, this webinar, and also this group, because we're all in a worldwide social media too. So suddenly, I have people already started asking about this India group, from CDAC and from MEITI in India, and also as Shivam said, the IIT Madras teams, and there are some teams in Singapore and Europe and US, who are all just checking on what's going on as part of this group. So overall, this is going to be a platform for all of you to grow your skills and demonstrate your presentation skills as well as the technology skills worldwide while you are studying in an institute here locally in India. So with this, I'd like to conclude my session here. And also next week, there is going to be a good presentation around the same, the same day, but Thursday, but it is going to be at 8:00 p.m. Indian time, because the other person is from San Francisco. He is actually, in a Pacific Standard Time, and, his time is going to be around 7:30 in the AM. So that's why, to adjust that, I moved the time a little bit later, but the presentation is going to be very good. He is going to be sharing some of the cool things, about chiplet and DARPA, how DARPA funded his agents. DARPA is an agency from US who funded, some of the, sponsorship, to the company and the other stuff. He's also a CEO for a company called Broadpack. So wait for it. You will get a message about, already we socialized, some of the information, about the webinar for the next week. Do join and collaborate on this platform. Thank you to all the participants as well as, the presenters, who really spend some time on putting together presentation and, presented here. Thank you to all. And let's get back, next week and, continue our education as well as, collaboration. Thank you.
Sir, sorry for interrupting. There is one more question.
Oh yeah, go ahead,
want
please.
me to try answering?
Yeah, go ahead, please.
Okay. Yes, so I'll try to share this web page here, which might make things clearer for you. So see, basically, in an ISA, you can define everything, right? A modern day processor is not just about addition, subtraction, division, multiplication. There are a lot of things. So even say x86 processors, which most of you would be having in your systems, they support a lot of novel ways of handling data. For example, you can say at a time do matrix multiplication in just one instruction. For example, your GPUs do complex operations like that. And again, when you go down to say something like a microprocessor, say something like Arduino, which is also a processor, but is at a very small scale, it's a microcontroller. So it obviously would have a limited functionality. And it doesn't really need to support something like matrix multiplication, because that would make its cost higher, its structure more complex and things like that. So to handle things like this, like making right from a microcontroller to a supercomputer, RISC-V has split the whole ISA definition into multiple extensions. So RV32I is the basic one, which is integer operations, which is like basic ALU operations, logical operations, and memory load store. Then M has multiplication, division, as I said. FDR for floating point, and then similarly you have many others for specific features which depend on the application where your processor will be used. So say something, when you have a microcontroller, you would have just like RB32I or RB32IM at max. But when you're building, say, a desktop level PC, you would need floating point and other extensions. So it works that way. I hope that explained it better.
Yeah, good. I think,
Thank you,
yeah. Thank you, Shivam. Good interest, people have actually. And these are all very important. And now again, the Shashank, we are adding things on top of this. ARM process supports switching between thumb state and 32-bit state. Thanks, Shashank, for that, for the response too. Thank you. And thank you all for all the participants again, as well as the presenters. And let's meet next week, next Thursday at 8 p.m. as part of this OpenPOWER hardware collaboration. Thank you all.
Thank you, sir. Thanks everyone for
Thank you. Thank you.